In this short video we're going to try and illustrate what is meant by the Chelate effect and why reactions involving this are particularly favourable and the complexes formed are stable. Now chelate comes from the Latin for a claw, as in a crab or a lobster, and we can see the sort of idea that this pincer movement, which is illustrated when we add the bidentate ligands around the metal ion. Let's have a look, using this example, why the chelate effect makes reactions so favourable and their complexes so stable. The first thing it's asking us to consider is the enthalpy change for the reaction. Now, we're not going to be able to know the number of this directly. What we want to try and do though is decide whether it's likely to be an endothermic reaction or an exothermic reaction, or isn't accompanied by much of an enthalpy change at all. So I've drawn this reaction out again, illustrating a little bit more about what we've got in terms of the complexes. So to decide whether this is endothermic or exothermic, a good place to look is the bonds that are broken and the bonds that are formed. So in this reaction taking place, these are the bonds that we're going to break in the ligand substitution reaction. So 6 nickel nitrogen bonds, and the nitrogen for an ammonia molecule. And the bonds that we're going to make, well, we've also got 6 nickel nitrogen bonds attached to a different molecule, admittedly, but I think from that we can say that there's not going to be a staggering enthalpy change in this reaction, and so delta H will be approximately 0. The next thing to look at is delta S. So this is in the topic entropy, and this is to do with the disorder of the reaction. There's several things that we can consider with this. So it might be whether things are changing from solids to liquids to gases, or it might be to do with the number of moles involved. Now we can see for our reaction we're going from 4 moles on the left hand side, so our complex, and 3 moles of the ethane diamine, and we're ending up with 7 moles of product. So we can say that this reaction is accompanied with a large increase in disorder, i.e. things are becoming considerably more random. The upshot of this is that delta S will decidedly be positive. And finally, tying this together and thinking about delta G. Now delta G is the Gibbs free energy change, and this will tell us whether a reaction is feasible or not. And to decide this, all we need to do is look at the sign of delta G. So if delta G is positive, that means the reaction will not take place. Whereas if delta G is less than 0, then our reaction is said to be feasible. If you haven't come across the expression yet for delta G, it's represented by delta H minus T delta S. So let's have a look at the components that we have. Well, our enthalpy change, we said, was going to be approximately 0. Our entropy change was most definitely positive, and we've also got the temperature, which we haven't mentioned. The temperature is recorded in Kelvin, therefore is always positive. So what that means for us is that we've got something which is approximately 0, take away something which is most definitely going to be positive, which means our delta G here is always going to be negative, which means our reaction will always be feasible, and hence the product is very stable.